the tone, please state your name followed by the pound sign.
And
your line has been muted.
4 per year. We collected a lot of input from the Aqua Watersheds Committee to help us get started on thinking through what the topics we'd want to cover with this series would be. And so we appreciate the input from people who responded to the survey we sent out and who have spoken with Tracy and Tom in the past to collect and gather some ideas. And I also wanted to give a few thank yous to begin. One to our planning team for this webinar series. Really appreciate all of the input that people have given. It's a group of state and EPA folks who have spent some time working through, thinking through the topics that we're going to cover, how we're going to format and structure the content for this and for future webinars. And also I want to thank Aqua and Julian, Tracy, and Tom specifically for allowing us to make use of this time, which is normally the Aqua Watersheds Committee monthly call time. We knew we'd have a captive audience, so it seemed like a good time and a good fit to have this session. So one of the questions that I'm sure will come up at some point is whether this session will be recorded. It will, and it will be recorded and available on our website, and we'll send out a link through all the same listservs that we sent out the announcements about this. So stay tuned for that. It will be coming eventually. And speaking specifically to questions as well, we're going to be taking questions in the chat and Q&A boxes, which should be in the WebEx software client that everyone has open. There's both Q&A and a chat box. So I will be monitoring those while our presenters are going, and then I'll try and collate and ask a couple specific questions when we get to breaks between presenters from those chat boxes. And then at the end of the presentation, if there's still time, we may try opening up the phone line, which is always risky with this many people on the line, but I would request that in preparation for that, people mute the line on their ends as well, even if it's automatically muted at this point, so that we don't get a massive sound once we unmute the lines. Questions that don't get answered, we're looking into consolidating those and then writing up written responses afterwards. And if there's anything that you realize you wanted to ask and you forgot to enter it into the chat boxes, there's going to be a post-event survey that's really short. It's about 3 to 5 questions, 3 to 5 minutes, and we would request that everyone fill it out. And there's one of the questions in there asks about any additional questions that you might like to give to the presenters for today. So yeah, I will give a reminder about that survey at the end, and we'd appreciate your feedback on that. It'll help us make future webinars even better. And finally, if you're having any technical issues, please send an email to me. The email address is dpeckham, that's D-P-E-C-K-H-A-M, @neiwpcc.org, or put that in the chat or Q&A box, and I'll be watching for those. So for instance, if you're having trouble viewing the presentation or something like that, we'll see what we can do to help out. And any future input, please send to myself and also to my colleague who's here in the room, Jasper Hobbs, which is JHOBBS @neiwpcc.org. And we'd really like to get any feedback on how to improve this series in the future. So thank you for indulging me on the housekeeping items at the beginning. And with that, I'm going to turn it over to our presenters for today, Kevin, Caroline, Jim, and Roger. And you've seen the flyer. The title is Modeling Applications to Integrate TMDLs and Permitted MS4s, and I'll let them take it from here.
Okay, thank you, Dan, and thank you for everyone joining today. So today we kind of hope to go through and really emphasize the permitted MS4s. So, you know, MS4s in general can cover both permitted and non-permitted. I think our emphasis today will be on the permitted aspect of it. So I'm going to start the presentation off and give some background information on kind of the TMDL and the whole basin scale TMDL modeling, and then how that gets linked in with the municipal scale analysis and implementation, and go over some of the implementation approaches that we've designed in Wisconsin. And then Caroline Berger is going to go through and explain the wind SLAMM model and how that's been developed, how it can be used in the implementation of these TMDL type analysis once you get to the implementation phase. And then Jim Bachhuber is going to also cover some specific examples of some modeling analysis that has been done for TMDL compliance. And then Roger Bannerman is going to finish it up by going over how SLAMM was calibrated and verified, basically cover, how this can be used in other states across the country, and then also really spend some time looking at new research, which includes the seasonality of loads and emerging new practices and techniques for controlling loads. So to start out is, what is a TMDL? And the best quote I saw was from Dean Moraldo when he was the Region 5 coordinator. It's, a TMDL reveals the skeleton in the closet, and usually we found, as we developed TMDLs in Wisconsin, it normally just wasn't one skeleton. And as an example, so currently Wisconsin is developing some large major scale TMDLs covering the Wisconsin River Basin, Upper Fox, but we started out with the Rock River and the Lower Fox, and both of those areas had substantial urban areas. So as we developed those TMDLs and we're doing it on a basin scale analysis, we started to run into some challenges with how to link that TMDL analysis we were doing with the implementation that was going to follow. So, quickly I think everyone on the call should know exactly what a TMDL is. It's that total maximum daily load that's broken into the load allocation, waste load allocation with a margin of safety. And then that waste load, that load allocation, again, broken into a waste load allocation and load allocation. We'll be emphasizing on this call the permitted MS4s, but the load allocation also includes a set aside for those non-permitted MS4 areas. So a definition of the MS4, it's the conveyance system including the roads with the drainage systems, municipal streets, catch basins, curbs, gutters, ditches, constructed channels, or storm drains. They are owned or operated by a municipality. And a lot of times I hear the term MS4 misused because they always imply that the municipal area that's permitted is an MS4. Again, an MS4 can be part of a permitted or unpermitted municipality. It's just that drainage system is owned or operated by a municipality. It is also not a combined sewer system and not a publicly owned wastewater treatment works. So another thing with the TMDLs is obviously the TMDLs must have an expression of the allocation on a mass basis. And this is one of those skeletons in the closet that came up because when we were working with our MS4s, it doesn't rain every day, it doesn't rain every week. So when they were seeing allocations on a daily basis, they were really struggling with exactly how they're going to meet them. They're like, well, we meet them on the dry days, and on the wet days, we don't. But a TMDL can be implemented on different time steps. And right now, as Caroline goes through the SLAMM model, we're using an annual implementation, but Roger will be touching on research which eventually we will be moving toward a seasonal implementation, especially when you look at the phosphorus loading patterns of spring and fall being the dominant time periods for phosphorus loading. I kind of want to cover the allocation approach because this gets to be critical in how we've kind of set up this modeling approach to address the MS4s. So the allocation approach, and the best way we found to explain it so far is that you have the two pie charts, and the total pie chart, that total area of the pie chart represents the load, the allowable load. So you have a baseline condition and you have an allocated load, which is the assimilative capacity. And what we've done in Wisconsin is used a proportional reduction methodology based on that baseline condition. And I think what's important to take away from this slide is that term baseline. It's not an existing load, it's a baseline load based on regulatory requirements and obligations. So one of the things we struggled with in our early TMDLs was defining that equitable baseline condition. And so this slide kind of goes through and explains how we approach setting that baseline condition. So again, the baseline isn't exactly, it's not the existing conditions, it's what our different sources have to do based on existing requirements. So looking at traditional wastewater treatment plants, they fall under the NR 217 requirements. So we had technology-based limits for phosphorus, for example, for those facilities. And when we look at our MS4s, our permanent MS4s, we had requirements in a rule called NR 151, which set performance standards that they needed to meet. On the agricultural side or non-point side, we also had mirrored this approach and have a series of performance standards. So when we look at the first step, the TMDL, we see where are these statewide requirements. If these are being met, where are we at with our pollutant load? Do we meet the water quality target? If we do, you know, we're done. But in most cases, those performance standards were not sufficient, so we do additional reductions from from that baseline condition. So again, kind of the terminology then that becomes important as we move forward with the next presentations, the part of this webinar is this existing conditions, this baseline and no control. So baseline, again, is what the stormwater or the municipality would be discharging if they met the NR 151 requirements. Existing is where they are at now relative to that baseline condition, and no controls is something that we have defined in our guidance, which lays out exactly what would that load be if there were no stormwater controls present and under certain road widths, for example, and certain development patterns. We have something called standard land use files, which really set that no control, so that if, for example, a municipality wants to start embracing green infrastructure and narrowing their roads and stuff, for example, you can get credit for that because your no controls is the standard development pattern. So a little background then on the NR 151, subchapter 3 covers these non-agricultural performance standards. We have performance standards for post-construction and new development, but the one that really gets pulled in for the MS4s is our developed urban area standard. And so we had promulgated a rule that required a 20 and 40% reduction in TSS that enters waters of the state. And this was done through a modeling approach. So all of our permitted municipalities, both phase 1 and phase 2, have gone through and done a watershed model. Most of them have used SLAMM. I think a couple use P8. But they use this model to evaluate where they are currently and where they are related to that NR 151 reduction goal. And then we set a series of benchmarks and timelines for them to get down to that reduction. And then, so that reduction, that 20 and 40% reduction, that serves as the baseline then for when we start the TMDL allocation, so that our municipalities have established either that 20 or 40% reduction. We know what that load is, and then if we need additional improvements, we start with that as that baseline. We have developed through this process extensive modeling guidance that kind of lays all this out. So here's just a screenshot of our website. If you go to it and just type in stormwater, you'll get to the stormwater homepage, and in there is a link to the guidance, and it lays out the different guidance. It lays out how to handle the modeling for NR 151. We have the land use files specified, and we have the different parameters in the model specified, which kind of puts the whole analysis in a certain box, so to say, but allows the consultants the flexibility to go through and run a lot of what-if scenarios and see what really works best for each source area within the municipality. So again, I kind of mentioned earlier that the model that gets used most is SLAMM, and then to some extent also P8. SLAMM, there'll be much more information coming on about SLAMM in a few minutes, but it has been used across the country, and a lot of the data that's used to support it is readily available, and both Caroline and Roger will be speaking on that. So I kind of covered what this important part of the TMDL analysis is this baseline. So when we started developing our basin scale TMDLs, there's really kind of 5 of them I wanted to touch on that had substantial urban areas in them. And right now, the Wisconsin River and Upper Fox are being developed, and they're labeled 1 or 2 on your screen. And those are using techniques that were kind of developed through the development of the Rock River and Lower Fox, which are 4 and 5. And then the Milwaukee is really, out of all of them, is the most urbanized area in Wisconsin, but it was also done slightly differently from the other versions in that HSPF model was used. And I'll cover that in a little bit more detail. So for those other TMDLs, apart from the Milwaukee, so when we were doing this basin scale analysis and setting this baseline in as starting point of loads for the MS4s, we ended up using what I would call a unit load approach. So initially, there was the thought of trying to bring in all the modeling that the individual MS4s had done, but there were reasons why that just wasn't going to work. So Jim Bachum and a couple other consultants had, between them, I think, modeled something like 30 municipalities. And when you looked at all that data, the loading rate, a unit load rate coming from all those established urban areas was very similar. And so we took what turned out to be the medium density residential no alleyway land use file from SLAMM, and the load that comes out of there on an average annual basis was within 1/100th of a decimal point of this average pollutant load that comes from all municipalities. So we kind of use that as a starting point for the mass analysis that's done at the basin scale. And then when we move to the TMDL implementation, we go with the full version of SLAMM, which allows a detailed approach looking at all the different land uses and the different loading rates that are coming from those land uses and different source areas. So really what this approach allowed is that we're using the same tool in the analysis, but at 2 different scales and taking advantage of the benefit of the tool at the implementation side. And to be honest, a certain element of luck came in where that medium density residential land use matched the average annual municipal loading rate municipality-wide. So when we do this analysis, like I said, the slide kind of shows that standard land use file, and Caroline will be kind of covering what the standard land use files are, but this is, again, medium density residential with no alleyways. And again, when we do this analysis, we break it out for permitted and unpermitted. And what we have here is how we adjusted those files based on whether it was permitted or unpermitted. And for the most cases, our unpermitted areas are the smaller municipal areas that tended to not have a significant amount of curb and gutter. So they were given a swale drainage. And then they start off at an existing condition, and then the baseline for the TMDL, again, is a reduction of 20 or 40% and the equivalent TP load for that baseline for the TMDL analysis. And one of the questions we've gotten early on from the consultants is, why didn't we just use the analysis that they did already? Because they've all modeled the MS4s, but one of the things is the rule NR 151 established a definition for what the established urban area was, and that doesn't necessarily encompass the entire city or village that would be permitted under the TMDL. So a lot of municipalities will be having to update their NR 151 analysis. Also, the time period used for the NR 151 analysis tended to be a 1 or 5 year simulation period, whereas the TMDL, we're doing the simulations to match the often 10 or 12 year period that's used in the TMDL. I kind of covered earlier about the Milwaukee TMDL, and it was a very large scale TMDL with 43 permitted MS4s and 12 general permits. It's important to note that we don't differentiate our requirements between our permitted, individual permitted and general permit MS4s, and we also don't differentiate requirements between phase 1 and phase 2. So in this case, the TMDL analysis was a little different in that the urban loading analysis was performed using a model called HSPF. And it was part of a previous study that was done for a regional water quality management plan. But one thing that came up early on is that HSPF didn't differentiate between the different source areas to the same extent that SLAMM does. So Roger and I both worked with the consultants that were working on that project, and what they ended up opting to do is to take their HSPF model runs. They actually ran everything twice. They ran the entire municipal area in SLAMM and then calibrated HSPF to SLAMM. You know, there are other ways that could be done. You could have just taken the SLAMM output files directly and then routed it through the receiving system, but in any case, they decided to calibrate HSPF to it. So again, we were able to account for this source areas and stuff that I think you'll see are very important as Caroline goes through part of her presentation. Another thing that came up in the Milwaukee project was addressing combined sewers. And I know this is an issue across the country. And so in Wisconsin, only portions of Milwaukee and Shorewood, which is a suburb located just north of Milwaukee, are covered by combined sewers. Now, one thing that was interesting is when we did detailed SLAMM analysis of that combined sewer area, because all that stormwater runoff was being captured and treated by the wastewater treatment plant, there was actually a 95% reduction in the stormwater loadings that were going to the receiving waters. But obviously the issue with the combined sewer is that combined sewer overflows. So Milwaukee Metropolitan Sewage District had embarked in constructing a deep tunnel system, which on average now there are about 3 discharges, just under 3 discharges a year under extreme events. And those CSOs are regulated under Milwaukee Met's permit, and that permit includes a long-term control plan with the elimination of CSOs. So when we went through and addressed the CSO aspect in this TMDL, they were not assigned a waste load allocation because the permit assumes that there's going to be an eventual elimination of the CSOs through their long-term management structure. So kind of moving into some of the key implementation things as we move forward and where SLAMM then really, or that matter, a modeling technique really helps is, so for each TMDL, obviously, we identify the permitted municipality and assign a waste load allocation for each reach and municipality. And then as I think we're all aware, once EPA has approved the TMDL, that next permit issued must have an expression of the waste load allocation. So, and what I have here is just the calculation of the % reduction from baseline. So when we set that waste load allocation, we can then go back and compare that to the baseline loading condition and calculate a % reduction that's needed for the municipality to meet the TMDL. And so we've gone forward with an implementation strategy of using the % reduction, and there's a couple reasons for that. One of them is the aerial extent of the MS4s and boundaries don't always match what was used in the TMDL. The municipalities, there's a constant expansion or change in some of the municipal boundaries, so it's really hard to get the exact boundary set. So this % reduction approach allows flexibility in addressing changes in the municipality. Another big issue is at the basin scale, storm sewers significantly change what might look like surface topographic breaks. So the % reduction allows you just continue to apply that % reduction to that reach shed regardless of how the boundaries change due to storm sewers. And then a couple other things is that this % reduction framework, we already had it in place as part of NR 151. So it was something that all our municipalities were comfortable with and had been engaged in. So most of them just had to take, or are taking the models they already have, maybe expanding them a little bit to include areas that previously weren't incorporated, and then checking to see where they are in relationship to the % reductions from the TMDL. So one thing I mentioned earlier is that we have this 20% reduction and 40% reduction. And so the guidance outlines both requirements, and again, everything's measured from a no controls, so that we expressed it in the same terms that NR 151 had it laid out. We had to do 20 and 40% because our legislature repealed the 40% requirement. So we have TMDLs that were developed before January 2012 that had 40%, but now all of them are starting at 20% baseline. The implementation of the percent reduction framework, what happens is the municipality goes through, does their analysis at no controls, applies that percent reduction, and they get the total mass that they need to reduce to meet the TMDL. And that mass stipulated might be different from what's in the TMDL wasteload allocation for numerous reasons because of the different scales of modeling. There's multiple aspects that come in, but in general, we found going back through is they're within percentage points of each other, very close. And then what the MS4 does is go through and see, where are we at in relationship to these needed reductions, and they start moving forward with a plan. The TMDL reduction or compliance then, and this was something that was maybe a little difficult, I think, for a lot of municipalities to grasp initially, is that the TMDL reductions are modeled or simulated predictions of the reductions needed to meet water quality. So a lot of municipalities thought if we meet these percent reductions or we meet these wasteload allocations, we're in compliance and we're done. But in actuality, it's the ambient stream monitoring that is going to be needed to delist the water body. So ultimate compliance is with delisting the water body. And then TMDLs don't acknowledge this concept of maximum extent practical, where the TMDL is set to meet water quality standards. So if a municipality says we can only get to, let's say, a 50% reduction, and the TMDL calls for an 80% reduction, there's not the use of a maximum extent practical where they can say, oh, we're done at 50%. So what we were able to negotiate with EPA is an extended compliance structure that allows MS4s time to meet the TMDL goals. And the best way to meet those is through redevelopment. And so how we set up the compliance is that the MS4s will have benchmarks that they set for every 5-year permit term. And those benchmarks are going to be identified in each permit. And to some extent, the MS4s will take a very active role in establishing what those are. And those benchmarks can be a combination of practices that are simulated in SLAMM or other practices that may ultimately get us to the water quality standard. And those specific requirements are laid out in the permit. And so, again, I mentioned earlier that our permits, whether they're phase 1 or phase 2, are all the same. So starting out, the first permit term that the TMDL is approved is the municipality goes through, updates their storm sewer map, and identifies any areas that should be excluded or included that were not originally included or excluded in the TMDL. Then they start going through and do their SLAMM analysis and provide a summary of where they're at in relationship to the TMDL reduction. So basically, what's the existing load? And then they come up with a plan to show overall progress in meeting those TMDL reductions. And again, if you're interested in seeing more about our permits, that's also on our webpage. So if you go from the Stormwater site and just click on the permits, that'll take you to this website. So with that, I'll be handing off to Caroline, who will be covering the SLAMM analysis. I'd also like to thank both Dave Werbach and Bob Newport from EPA Region 5, who worked with us extensively to develop this approach and sat on an extensive team we had that I think Jim was on it. We had municipalities from around the state who helped develop this approach. So, Caroline? Dan, did you have any questions that you wanted to address right now before we move on to Caroline?
I've been monitoring the chat boxes, and I have not gotten any specific questions yet. I would encourage anyone who does have questions to enter them into the chat boxes. But yeah, for now, we can move along to Caroline.
Okay, thank you.
Hello, this is Caroline Berger. One of the things the committee that put together these webinars said that people might be interested in is the tool that we use when we are doing all this modeling work for the MS4s, for compliance with the TMDLs. So I'm going to spend a little bit of time briefly explaining the tool, how it works, and that it's not really a Wisconsin tool. It's literally actually applied all over the world. So the DNR, after a lot of development, identified that we can use for our work, we can use WinSLAM, P8, or an approved equivalent. And as Kevin went through, the reason why this works for all of our communities is they've developed this guidance and standards that gets everybody on a level playing field. So when they're doing the modeling and putting together the plans, everybody kind of starts out basically on the same ground, and then you build from there. So nobody is being penalized, and if they're maybe already going above and beyond. And over 95% of the MS4s in Wisconsin, they just happen to use WinSLAM. And I think one of the reasons why is that it provides the most flexibility. You can run the most what-if scenarios to see how you can implement the most cost-effective scenarios to meet your compliance requirements. So what can WinSLAM do? Why would you use a model? Why wouldn't you just use the standards that the DNR has in place? Well, it can tell you the actual sources of where the pollutants are coming from. It can tell you where the pollutant loadings are for different land uses without any stormwater control measures in place. It can tell you how these things change as development increases. So say low density development to medium density development to high density development. It will tell you what different stormwater control measures will do. And then you can put in various treatment trains of stormwater control measures to meet the regulatory requirements and the cost to find out what will help you meet the requirements with your least cost option. And then basically say it in a different way, which drainage areas generate the highest versus lowest loading, and we have some graphics later that give an example of that. How much pollution control do individual treatment systems achieve? If, as Kevin said, you need to reduce phosphorus by X%, how can you do that? And then LID, green infrastructure, those are also very important tools in our toolbox. WinSLAM can also evaluate those. So what can't you do with WinSLAM? This is very important. It does not evaluate the runoff volume from snow melt. So for areas of the country that do have winter, where it snows, the snow stays on the ground through the winter, and then it melts in the spring, it does not evaluate the runoff volume from the snow when it melts, but it will evaluate the pollution load left on the ground after the snow melts. It also does not evaluate base flow conditions in the stream. It generates the urban pollution load to the stream, not the runoff volume that is present in the stream during dry weather conditions. It doesn't do in-stream processes, so it will not route your pollution loading through a river or a lake. It does generate hydrographs and particle size distributions, and it does route them through the control practices, but it doesn't do complete routing like SWIM does with the St. Venant equations. It doesn't do construction site erosion, so it is a developed urban pollution modeling, and it does not do design storms, so your SCS type 2, 100-year storm, not that type of model, and also is not an agricultural model. So what can it evaluate? This is a list of some of the pollutants it can evaluate. Runoff volume and TSS are always evaluated, and then you can add these other pollutants. And if you have data for a pollutant that is not on the list, you can add that pollutant. You can basically create your own pollutant file and then also evaluate that through the various stormwater control measures that are in the model. So what stormwater control measures are in the model? This shows a list: wet detention ponds, porous pavement, street cleaning, catch basins if they have sumps and they are cleaned, grass swales and filter strips, biofilters, bioretention, infiltration, green roofs. We just added media filters, and then beneficial uses like reuse, cisterns. So these are all these stormwater control measures are in the model, and they all use their processes and then the research data that has been collected over the years to evaluate their effectiveness. So where did WinSLAMM come from? It started its development in the 1970s, and it actually stemmed from street cleaning. And then it slowly grew through basically lots and lots and lots and lots of research. And Roger Bannerman, who's going to speak last, is intimately familiar with a whole bunch of this research. And then the first Windows version was developed in 1995. In the 2000s, we moved it from a text-based version to a data-based version, and very, very soon it is going to be compatible with GIS, and it is continually being updated with research data as it becomes available. So why is it unique? Well, it's based on actual monitoring data. So the results that you get really do match what you get in the field, assuming your rainfall files are what actually happened and your drainage areas are what actually happened. In the initial versions of the model, they focused on site hydrology, but over the years, it's moved from specific sites to now we're modeling huge watersheds, we're modeling municipalities for TMDL compliance, et cetera. So we're going to summarize this. It uses local measured continuous rainfall data. You get it from the airport or a rainfall gauge that has this data, so you're using your data. If you're in San Diego, you're not going to use a Wisconsin rainfall file. It generates pollutant concentrations, runoff volumes for each source area for each rain event. And the stormwater control measures in the model, they're simulated using actual processes for each stormwater control measure. So you're not saying my pond gets 80% and then the model will sit back, oh, the pond got 80%. It's actually going to evaluate the pond using Stokes' law or the runoff volume particle size distribution going into it based on the land uses that are upstream of it that generated that runoff volume. So the model is all based on small storm hydrology. And some of the various states' stormwater manuals do use a subset of small storm hydrology. They don't go as detailed as it, but they do use a little bit of it. So as we're going through it, depending on the state you're from, you might recognize some of the equations once we show you those. But small storm hydrology is basically the concept that the smaller and medium-sized rainfall events generate most of the stormwater pollution. So the small rains, the smallest ones, typically less than ½ an inch, they account for the largest number of rain events. And ideally, if you could, you would infiltrate these so that they would you'd essentially eliminate the runoff from these in an ideal world. And this is all from Dr. Pitt's research. Dr. Pitt is the main author of, the original main author of the model. The medium rainfall events, so typically from ½ inch to 2 inches, depending on where you are in the country, are responsible for most of the pollutant mass discharges. So in this category, you want to either capture them and infiltrate them if you can, but once you get more towards the 2 inches, it's hard to infiltrate something that large, so then you're going to move more to the treatment of it instead of infiltrating the entire thing. And then the large ones, these are more what we would think of as our design storm events. Those are not cost-effective to treat in terms of stormwater pollution reduction. And these are typically the events we think of when we think of flooding. So we want to make sure that our wet detention ponds and our biofilters can handle these and not be hurt when they come through them. But they're not necessarily going to fully treat all the runoff from, say, a 100-year event. And so then again, this is just reiterates small storm hydrology, and the reason why we reiterate this so many times is because a lot of stormwater practitioners, when they start their careers, they started with design storms, and so when we move into wind SLAMM modeling and water quality modeling, we're moving away from the concept of design storms to continuous simulation, looking at the smaller storms, because most of the pollutants from stormwater runoff come from the small and medium-sized storms. So this just shows what we were talking about in graphical form. This shows a plot of almost 4,700 rain events in Baltimore, Maryland for a strip mall from 1953 to 1999. And from ½ an inch, remember one of the slides said about 75% of the runoff volume comes from the medium-sized storm events. So if we categorize our medium-sized storm events from ½ an inch to about 2 inches or so, you can see that that 75% approximately is generated from the medium-sized storm event. So if we can treat the storm events 2 inches or less, we're going to get about 80% of the runoff volume treated. So this essentially is the concept of small storm hydrology, sort of in graphical form. Oops. And then from small storm hydrology, then because we're looking at each of the rain events, the very smallest to the largest, but also comes out of small storm hydrology is that within each land use, and then within each land use are all these source areas. So within residential, commercial, industrial, institutional, you have roofs, parking lots, sidewalks, streets, landscaped areas. Well, a parking lot in a residential land use generates a different concentration than a parking lot in a commercial land use. And we know this because of all of the research data that's been collected through the years. So when you do your wind SLAMM evaluation of your municipality, and you're modeling your parking lots and your roofs and your sidewalks and all these different land uses, the model is calculating the runoff volume and the pollution loading for each of these source areas and each of these land uses, and it's calculating the different runoff volumes and pollutant loadings, and they're all different concentrations. Okay, so for those of you that like equations, we're going to show you the equations quickly. But again, this is, so the model is built on source areas. So your roofs, your sidewalks, your parking lots, your landscaped areas, and then it uses what we call parameter files. So your parameter files are your rainfall file, which is your local rainfall file. So if you live in Boston, Massachusetts, you're going to use a Boston, Massachusetts rainfall file. And then this next set of files have all been calibrated based on different parts of the country. So if you're in Texas, you're going to use a different file than if you're in Florida. And so this shows the different parts of the country that these files have all been calibrated on, based on Dr. Pitt's work. And so you can see there's files for the East Coast, Southeast, Great Lakes, Central, Southwest, and Northwest. And these come out of the National Stormwater Quality Database, plus the work of various researchers. Okay, so here's the guts of the model. And again, for those of you in other parts of the country, you're going to recognize some of these equations because when you're generating your water quality volume that you have to treat, this in some place is the equation that you actually use. So it's simply to calculate your runoff volume, it's your rainfall depth times the area of your source area, so your roof, sidewalk, your grass, times your runoff coefficient, times the unit conversion. Now what makes wind SLAMM different though is it's doing it for every single source area for every single rainfall event. So there's a different runoff coefficient for a half-inch rain for a roof than there is for a 1-inch rain or a sidewalk. And that all came from all the years of research that's gone into the model. And so this shows a graph of the rainfall depths on the bottom, runoff coefficients on the side, and then you can see in the legend some of these source areas in the model. And so you can see how they change as the rainfall depths increase. So your rough textured streets have different runoff coefficients and change differently than, for example, your pervious areas with clayey soils. So first the model will calculate the runoff volume. Then it will calculate the particulate solid loading, or TSS, or sediment, depending on what you like to call it. So it's the particulate solids concentration coefficient times the runoff volume that it calculated previously times the unit conversion. And it does this for every single source area in every single land use for every single green event. So just like the graph I showed you previously, there would be another graph showing how it varies for source areas or land uses or the particulate solids or sediment or TSS, whatever term you like to use. And then again, the pollutants. So then once it calculates the runoff volume and the sediment, then it will calculate the pollutants. And there are two different equations depending on if it's the dissolved pollutant or the particulate pollutant. If it's the particulate pollutant, it's going to use the particulate solids loading that it calculated times the pollutant probability distribution coefficient times the unit conversion. If it's the dissolved portion of the pollutant, then it's going to use the runoff volume times the pollutant probability coefficient in milligrams per liter times the unit conversion. And again, these coefficients are based on the research data that's been collected for each source area. And again, it does it for each source area, in each land use, and each rainfall event. And then what it'll do is it will, once it calculates it for all the source areas, for all the land uses for the rainfall event, then it'll summarize it, and it sends it on down the network to the stormwater control practices. And then there are the particle size distributions and the hydrographs. And so one is generated, these are also generated through the modeling, and they are modified, both the particle size distributions and the hydrographs are modified as they are routed through the stormwater control measures. So depending on what type of stormwater control measure it is, say if it's street cleaning, that may only take out the larger particle sizes. So streets are cleaned, and then that resulting particle size is then maybe sent to a wet detention pond, where then the wet detention pond will receive the resulting particle size distribution and the hydrograph, and then further treat the stormwater runoff. And the model has a time step of all the calculations that it's doing. It's 6 minutes is the default. You can change that if you need to. So building a model file, this shows an example of the data you put in the model file. It's the same data that you use to build or analyze anything that you would need to analyze for TMDL compliance, any type of stormwater management plan, WIP. You're just categorizing it in a way that SLAMM would understand. Your drainage areas, your land uses, these source areas and source area parameters we'll get to on the next slide, and then your stormwater control measures. So what is the municipality doing already to treat their stormwater, or what are they going to do to treat their stormwater? Now you might be saying, wow, there's no way I'm going to collect all the sidewalks and roofs and driveways for my municipality. That's just way too much. So one tool that's been developed by Roger and others are standard land use files, and Kevin touched on this a little bit. So these are files that work within SLAMM, and they are 100-acre unit files that represent typical land uses that you would see in a municipality. So there are files, for example, 100 acres of medium density residential, 100 acres of medium industrial, 100 acres of a park, 100 acres of a shopping center. And so we use these files so that we don't have to measure source areas and whether or not they're connected or disconnected. Now, when we use these in different parts of the country, for example, we did a project in Calgary, or parts of the world. We did a project in Calgary, Alberta, Canada. Their high-density residential was a lot denser than our high-density residential. So we created a Calgary high-density residential standard land use file and use that. So these are here as a tool to help you do your analysis more efficiently, and they are acceptable for when you're doing larger planning level studies like TMDLs. If you're doing a site development or just looking at if you're designing a green roof and you want to know how thick your substrate needs to be, well, you would just put the roof in. There would be no reason to use a standard land use file. But if you're modeling a large watershed or a large municipality, then we use these standard land uses to help make our analysis more efficient. So what do we use this for? A single source area. So we're designing a parking lot biofilter. We would put the parking lot in the model, and then we would size our biofilter to treat whatever pollutant or infiltrate whatever pollutant we need to the site. So a 40-acre residential subdivision is going in, and we need to meet a volume reduction requirement. Or a watershed or a municipality. So we're putting together a stormwater management plan for TMDL compliance for several municipalities. We're using SLAMM. And this graphic shows you an example of the kind of output that we generate from the SLAMM results, where we take the pollutant loading generated from the model and we tie it to GIS. And in this case, the more red the areas, the higher the pollution loading, the more green the areas, the lower the pollution loading. And so we can show our clients, you're going to want to concentrate on the areas of red to reduce your pollution, because that is going to be more, generally that's going to be more cost effective than concentrating on areas of lower pollution loading. And then again, more types of projects, again, green infrastructure and low impact development. Those are very important tools in our toolbox to help us meet TMDL compliance. So we're using the model for both those. New development and redevelopment in Wisconsin, municipalities, municipal engineers require their consultants to use either P8, SLAMM, or approved equivalent to show that they're meeting their ordinance. And then the alternatives analysis and stormwater control design. When we go to the next level from planning to design, we use SLAMM to make sure that we're still achieving the goals that we wanted to achieve with the actual outlet structure and configuration that we are putting out in the field. And as the model grows and as our users grow, we add more and more types of output. A lot of the output available in the model is a result of our users and what they want to see, what they need to see for their regulatory compliance. So this list shows you just a few examples of what you could get out of the model if you needed it. And then we're always adding more pieces depending on what our users need to see. And with that, Jim Bachhuber is next. I didn't know if there were questions for Kevin or I in the meantime.
Yeah, I've had a couple that have come in, so I'll try, and I think that some of them were answered as we continued on through the presentation, so I'll try not to ask those ones, but for those who entered them in the chat box and you had a piece of the question that you don't think was addressed, and I skip over it, please let us know in the survey at the end, and we'll make sure that we get exactly what you want answered. So two quick questions for Kevin, clarifying questions. One was what municipalities specifically were talking about for this webinar. And then the second question was just for clarification point, confirming so that the MS4s baseline is always equal to the TMDL allocation, or is that not always the case?
Okay, so I'll start with the second question, that the baseline that's used for the TMDL is always set at that NR 151 requirement, which would be that 20 or 40% reduction. So what Caroline just covered, all our municipalities have gone through and done this analysis. And so that 20 or 40% reduction is applied to those municipalities. That resulting pollutant load is used and then fed into the TMDL analysis to say, are we meeting water quality standards? And then if we're not, we start a proportional reduction going down from that baseline. So the baseline always starts at those NR 151 requirements. As far as the municipalities, I think the emphasis on this presentation is the permitted municipalities, because again, they have a permit, so when that TMDL is completed, the requirements of the TMDL appear in their next permit. So they have a very defined implementation schedule. The non-permitted MS4s, the analysis is included in the TMDL, but that gets included under the load allocation. And in Wisconsin, like I imagine in many other states, that ends up being more of a voluntary compliance. Wisconsin does have some regulations, though, that show if a significant part of the load is coming from that non-permitted urban area, we can come through and permit them as a result of the analysis. So I hope that addressed both the questions.
Yeah, thank you, Kevin. And I'll try and take a couple more of these ones for Caroline. One very quick one is WinSLAM a public domain model, or is it proprietary?
It is proprietary.
And then a few more. So one, how could global warming, increased rain intensity, extreme temperature, or drought affect the coefficient you are using the coefficients you're using that are based on long-term data? Should these coefficients be routinely updated/verified?
You know, that is a really interesting question, and one I just talked to one of the engineers at the DNR about here, because our Atlas 14 that recently came out, and the rainfall files that for Wisconsin that were selected by the Wisconsin USGS, and they represent the average annual years of rainfall for different parts of the state, and that is what our DNR have said that we need to use for analysis. And so what this engineer at the DNR did was then compared the Atlas 14 numbers to the values that in the files that the Wisconsin DNR is requiring that were created by the USGS. And he found that, yes, for the larger, more infrequent events, they were bigger numbers, but for the smaller numbers, the smaller, more frequent events that WinSLAM is evaluating for the average annual years of rainfall, he didn't see a statistical increase. So he felt comfortable leaving the numbers as is in WinSLAM for the next foreseeable permit terms, 5, 10, 15 years. Will that need to be evaluated in the future? Likely, but for the next few permit terms, ours are about a 5-ish year cycle, they're going to stay as they are.
All right, thank you, Caroline. So mindful of the time, I know that there are a number of other questions that have come in, and we'll circle back to them if possible at the end, but I want to make sure we give plenty of time for our remaining two presenters. So let's move on to Jim for now, and I'll keep collecting the questions.
Okay, thanks, Dan. Appreciate it. This is Jim Bachhuber. I'm going to run through an example now of the analysis that was conducted for a particular city in Wisconsin. And it's just an example, but it's a real analysis, and a very similar approach is applied to all of our cities that are in a TMDL implementation phase for a project. And I include these pictures because they're pretty pictures of where I live, so that's the only reason for that first slide. Let me skip ahead, and again, Kevin covered a lot of this, but I think it bears some repeating. I'll try not to be too repetitive, but you know, stormwater permits here for MS4s are the same as throughout the nation. They all have the same 6 minimum measures, so that's no different. The TMDL requirements are the same language for our Phase 1 and Phase 2 MS4 permits. If you're in a TMDL, approved TMDL area in the state with an MS4 permit, you have this language about complying with load reductions, and most of our TMDLs so far have focused on sediment and phosphorus as the two major drivers for attaining water quality conditions and the impairments that are trying to be removed. The difference is we're talking about a numeric standard here for our MS4s, and the numeric part of that is a load reduction based on the approved model. A lot of TMDLs, a lot of permits talk about managing stormwater, and they're measured as a % impervious area or acres of impervious area managed under a certain kind of a practice. That's not the approach DNR chose to use here. It is a pollution load reduction based on a % control that Kevin talked about. And the reason this works is this last bullet here, and that is that the DNR has set up an extensive set of guidelines. I'm going to hit this a couple times. And what that does is, as Kevin said, levels the playing field so that all the municipalities are on parity, but also maximizes the flexibility which each municipality can do to figure out how best to comply with their own TMDL waste load allocations. And so there's a lot of different ways to approach compliance within each municipal permittee. So, you know, just as an example, this is just clear. This is just a generic example. If you had a waste load that said you had to reduce your pollution, whether it's sediment or phosphorus, let's talk about phosphorus, by 50%. The basic steps: figure out what your base condition level is. As Kevin said, that base condition is the pollution under meeting the former NR 151 requirements, which every city has to meet. So it's kind of think of it as kind of like a secondary treatment level for wastewater. Everybody's got to do that, and then there's, of course, more treatment above that normally is required to meet a water quality condition. But the first level of compliance is this base condition, meeting the NR 151 requirements. And let's say you had to reduce this by 50% to get to a certain TP phosphorus goal, and then that goal is set for each impaired water within the urban area, and you go about the practice or the effort of figuring out how to achieve that reduction. Now, I'm going to make this into a real example here, so I don't want to dwell on this slide. The guidelines that DNR has out there, again, they have, as Caroline alluded to, they have standardized rainfalls to use depending on what part of the state you're in. There's 5 different regions. The municipal land uses are represented by source areas, and these are defined on a standardized basis by the agencies. We use NRCS soil conditions for our infiltration issues. In other words, the hydrologic groups define our landscaped and non-impervious areas or pervious areas. We also have to step through for our cities and figure out where the regulated areas are. Not 100% of the municipal boundary is a regulated MS4 area, and I've already touched on these last 2 bullet points, so I'm gonna fly through that. So, basic procedure: we use the model, as we said, to come up with a base condition, which is what we talk about, meaning the regulations are being met. We use a model to calculate existing % control, and then which accounts for the current stormwater management measures that a city already has in place. And then we optimize proposed management, identify those measures to meet, let's say in this case, phosphorus reduction, TP, and then prepare a schedule for implementation. That's nothing very unusual. That's a pretty straightforward process. The unique part is that, in fact, it's done on a more objective numeric basis. So a case example here, just to walk through real quickly. I'm going to talk about a city in south central Wisconsin. It's Janesville. For us, that's a middle-sized city, 64,000 people. Here's the area we're talking about, and it's in this part of the state. The Rock River Basin is about 3,600 square miles. It covers a good chunk of south central Wisconsin. It's got, I forgot the number, hundreds of impaired water bodies in it for both phosphorus and sediment, and Janesville is just one small piece of the puzzle. But because Janesville is an MS4, it received its permit and its TMDL waste load allocations for phosphorus and sediment. And so this is a little close-up map of Janesville. This is the municipal boundary, the black line. The blue through the middle of the city is the Rock River itself. That kind of runs right through the guts of the city. The impaired water bodies are the Rock River itself from north to south. The entire water body is impaired, and then there's another impairment on a tributary to the east of the city. So those are the impairments that the city was facing. When the TMDL came out for the Rock River, it identified Janesville as one of the MS4s. Each watershed within Janesville received a unique phosphorus and sediment waste load allocation and a load reduction requirement. What you're looking at here in this graphic is some of the major drainage basins. These colored areas represent drainage basins. Each one, as I said, receives a waste load allocation requirement. This is a 49% reduction of phosphorus, and you can translate that back into pounds if you want to do the math. So each of these four major areas, there's actually 6 in Janesville. I'm just showing you 4 have unique requirements, and the city has to come up with a plan to meet these reductions then to meet the TMDL requirements. So the challenge is to come up with, are they meeting it right now with their existing management measures? If not, what can be done over time to close that gap and meet these reductions for each of these drainage basins? The first step we do with a city is to figure out what area is actually regulated. What is the MS4 regulated area? And I think there's some similarities across the country on this. For example, if you are a owner or land that drains directly to a receiving water body that does not go through a municipally owned and operated conveyance system, stormwater conveyance system, you are riparian, and that piece of land is not regulated by the MS4 permit. Okay, so we did figure out which lands were not regulated because they are direct riparian to the water bodies. Also within the city are areas that are permitted by or have their own separate stormwater permits, such as the DOT, this is an interstate going through the east side of Janesville. Well, that corridor is under its own stormwater permit, not regulated through the city's permit. And so they are going to comply through a separate mechanism, not the city's responsibility. We have areas in the city of Janesville, in this case, that are internally drained. This is an old quarry. It's kind of hard to get a view of this, but a lot of land drains into that quarry. It's abandoned. It's no longer functional, but it never gets out. It simply goes in and infiltrates. And so, again, these drainage areas are identified. In addition to that, we have regulated industrial areas, just like any other part of the country. So these areas have their own individual or general stormwater permit, but they're regulated separately by the DNR. And again, these footprints are not, the pollution loading from these footprints are not the responsibility of the MS4. Other issues may come up when you have illicit discharge or things like that. That's a different story. We're talking about normal stormwater runoff from rainfall. So keep that difference in mind. Other things, okay, so now we're on to accounting for the current stormwater management practices. We've cut out the areas that are not regulated from the MS4 permit. Now we go through a process to identify how well our current practices performing. The City of Janesville has a lot of existing stormwater practices that have been in place for various amounts of years. One of them is a large drainage system on the east side of town, which they call their green belt. This is not a channel. There's not navigable water down here. This is a dry bed, and it's essentially a very wide grass waterway that they've had in place for decades. And this grass waterway does function not only for open space and other purposes, but functions for water quality. And as long as it's maintained, vegetated, not eroding, and doesn't have gullies in it, if they can maintain it under that condition, it can count as an existing stormwater control measure. Traditional stormwater quality basins we account for that are out there. We account for non-structural stormwater management measures such as their street sweeping program, and can that be improved to help achieve more pollution control in a non-structural fashion. Those are just examples of practices that we account for. Once those are accounted for in the model, as Caroline was explaining, we're able to generate, using all the other factors that the SLAMM model uses, pollution loading conditions within the city, accounting for their stormwater control measures, and begin to focus in on areas that are high and low in terms of loadings to begin to identify control measures to reduce the gap. And I'll get to another slide here. So again, modeling is done to the base condition, defined by DNR. We repeated it a couple of times. I guess we should quit repeating that probably. And the starting point for compliance is this baseline condition that we've talked about. And then here's just another example of high and low loading areas after the analysis for their current condition was evaluated. So now we have to figure out what the gap is and what can be done to close that gap. We're going to identify these measures to meet phosphorus requirements, or maybe it could be sediment control. Usually phosphorus ends up being the driver here. It's just simply a more difficult pollutant to manage. Then we'll use a model to analyze which measures make the most sense and optimize their placement and locations, and develop a plan. I'm not going to go into the details of the management measures. It will take more time, and frankly, I think most of us have a concept of what kinds of measures are out there in the toolbox. But we simply did come up with a level of approach for each of these reach sheds. That's what we're calling these drainage areas to each impaired water body. And we want to maximize our current practices by making sure that the current practices they have are well maintained, convert some existing dry basins to a water quality pond, which has a more effective pollution control value to it. Every time redevelopment occurs in the downtown or elsewhere, maximizing stormwater management measures being integrated into those redevelopments, that helps move the needle toward closing that gap. And then incorporating practices into street reconstruction. The city has an aggressive street maintenance reconstruction program. When they do this, they can incorporate, and they intend to incorporate, stormwater pollution control measures as part of the street reconstruction projects. The plan itself identified about $7.5 million as an initial level of effort. It's not the full package, but it's a starting point. What we found was if we carry out those recommendations in the initial phase of the project, I'm just showing 2 reach sheds here. I'm not going to show you all of them, but we found that the original goal was a 49% reduction. Currently, with their current management measures, I'm up here on reach shed 71. They had a 36% reduction, so there was still a gap to close up to the 49 reduction. We found management measures to get us up to 42%. We couldn't hit the 49 under existing and all the other redevelopment type approaches we come up with. So there's still a gap remaining. In this one, down here on 73, actually the existing management measures are exceeding the requirement. They were supposed to be reduced by 64% from that baseline number, and with the management measures that are in place, they're already achieving that and a little bit better than that, okay? So, there is some excess here. There is some opportunity within the state because of the same water bodies that are being impaired to do some You might call them trading or at least balancing of these pollution control levels. And so there are some opportunities here to balance these two out, only because both of these watersheds are going to the same water body. That's the reason why that's an opportunity here for Janesville. But what I want to really spend a minute on is that the reason I think the modeling approach is important, and I'm not trying to sell the model. I don't sell the model. I know it's proprietary. It's a pretty nominal cost. We're talking a couple $100. You can go to the website and check it out. It's been used by almost every city. I think every permitted city in the state has the model. They have people on board who run the model, understand it, and can use it, and are using it for their own site developments to check against developers who are submitting site plans, et cetera, for a site plan. But the reason this works is we got this guidance from the regulatory agency to make sure everybody plays fair, and we're treating everybody the same throughout the state. Establishing these normalized base conditions for comparative purposes, as I said, leveling the playing field. It allows an objective measure of progress. It allows both the regulated and the regulators to look at and have a way to measure progress being made, and not just saying that we've got so many BMPs in place or so many control measures in place or we're sweeping more frequently or whatever. We can at least attach, albeit they are modeled numbers, but they are values that have some relative comparative purposes to say we're making some changes that have occurred over the last X number of years. And it allows this flexibility I talked about in that cities, as opposed to using spreadsheets or other more routine measures of approach, I think it enhances their flexibility from a city or developer or an individual point of view to really come up with the best solution for their particular local physical and other requirements within their sites, and achieve a number that can be compared to other sites that are being managed. The same approach is used. We're using sediment and phosphorus, and there's, as Caroline showed you, there's all the litter pollutants are incorporated in the model also. As you saw on that slide about where achievements could be made, there was a watershed where even with the retrofitting, we found that we couldn't fully achieve the pollution control requirements for that particular leach shed, according to the TMDL. DNR is allowing for plans that show progress and good faith effort, and that's where the modeling comes in, and a longer-term feasibility compliance through things like long-term redevelopment, new technology that we don't have now. I've been around the business now for 40 years. We didn't have these proprietary practices. We weren't filtering stormwater that long ago. We're using coagulants now, real-time controls, all kinds of things that weren't around 10, 15, 5 years ago. So they recognize that there's new technology that we may not be aware of today that may be available in the next 5, 10, 15 years. I think that's my part. Oh, I'm good. Dan, I don't know if you want to interject any other questions at this point or wait.
Yeah, let's keep with a couple questions. There's a lot there, and maybe we'll have some time at the end to go over them, but just to knock out a couple of them. So I did get a couple questions about having the webinar available for download, and the answer is yeah, stay tuned for that. We'll get to you later. And then for a couple of questions, one, and these three were coming during Caroline's presentation, and you guys can decide if you would like to answer them. Can the WinSLAMM model be used to document current pollutant loads on a watershed scale?
Yes. Yep. So when we do these analysis for TMDL or our local state stormwater requirements, first we look at what's coming from the watershed on a no controls condition, which is a predefined condition from based on our DNR's guidelines. And I think Most states have sort of the same thing. It just might not be as defined as what our DNR does. And then we look at what's out there right now. Are they street cleaning? Is there grass swales? Is there ponds? And then based on that, then we look at, okay, this is how far they are. How much farther do they need to go to meet their waste load allocations?
I'll just kind of add that, Dan, quickly. When you say watershed scale, the answer is yes, but the other caveat is that we're talking about urban watersheds. Would not be appropriate to use an agricultural watershed. Okay.
All right, great. Thank you, guys. So I'm going to ask these next two together. One is, did DNR require the use of a model, or did they provide training and outreach prior to requiring the use of a model? So was it just straight up a requirement, or was there some outreach before that? And then connected to that, how much resistance was there from MS4s to being required to do modeling? Was there a problem with their capacity to conduct the analysis?
So some of this predates when I came to the DNR, so I'm looking at Roger, because before Roger was with USGS, he was at DNR. So we did provide a lot of extensive training. So the rule, NR 151 was kind of rolled out in a couple phases, and so each phase we went through, we kind of added some additional requirements. And the modeling, initially there was resistance to the modeling. And the modeling is supported by, the guidance and these files and stuff that have been mentioned, but also our technical standards. We have technical standards that also support this, which explains like how to properly design a detention pond. So early on, when we developed all our technical standards, we always ended up giving the option of, here's how to do it in the model, and then here is some, like if you're not going to run a model, here's how to design the practice, and here's the credit you get. That being said, there wasn't a lot of flexibility in that, and often it was very conservative. So take, for example, wet detention basin. We can't account for all the different land uses, flow conditions, and everything that the model can. So we had kind of a standard ratio that came from literature of the size of the detention pond and how big it would need to be to settle out X% of a pollutant load. And so we had that in all of our practices because there was resistance to the modeling. But over time, what happened is I think a self-selection started to happen. Municipalities hired consultants who could do the modeling or had the modeling staff kind of build up in-house and started to see a cost savings to this and more flexibility. And now, I'd say in probably the last 10 years, we've moved away from this resistance of modeling and everything's done via the model. I don't think any of our regional stormwater staff see submittals come in anymore that just use the standard rules of thumb. Everything's modeled. So.
And we've never really required people to use the model. I mean, it just became something where we'd say an approved model like SLAMM, all right? And in my 40 years at the DNR, we went through many ups and downs with this, but overall, people realized that the model is being developed for them. And it facilitated TMDLs, it facilitated almost anything we did with stormwater. So overall, I got a very positive reaction through the years, and we've done a lot of outreach, and we run 2 workshops a year to help people use the model. And we're very responsive to questions we get. So so it is proprietary. There's a little bit of money charged for it, but you have to support a model. So that supports making changes and so forth. Good question. Very good question.
All right. Thank you, guys. And I'll do one more very quick question. Was a QAP, Quality Assurance Project Plan, I believe is what it actually stands for, required for the model for each municipality?
So each municipality doesn't generate a QAP because we kind of have all the standards laid out. We have the files laid out, the guidance documents, and so they just adhere to those requirements. We don't require the municipalities to put together QAPs. And then in the case of, let's say here, this TMDL analysis that's done on a municipal scale, they submit the write-up, and we have some standard methodologies for submitting that analysis. And then also the model itself. And the model is, you know, it's accounting for a lot of different things, but it's also, I would say, elegant. I would use the word simple in that the interface is simple, but I would say it's really elegant in that it's really easy to go through and check to see if the proper files are being used and stuff. So we've never developed or required QABs.
All right, thank you, Kevin. I got one more question asking about where the recording will be posted. So how we're planning to do it is have a subpage on NewEpic's website where it will be posted. So the link for that will be sent out to the various contact lists that we use that you guys found out about this from. If you want to make sure that you get it, feel free to send myself or Jasper a message. My email address is dpekham@neiwpcc.org, and I'll say that again at the end if you want to take it down. So the last question I get, well, pretty much I'll just use as a segue into the final presentation here for Roger. So the question was, has the monitoring data confirmed the modeling results from baseline to current conditions? And so maybe I guess if you can perhaps cover that as part of what you're covering for the presentation, I'll turn it back to you for the last section here.
Okay. You probably appreciate right now all the things the model does and the basic structure of the model. But with the model having the structure that it does, it certainly has presented me a challenge over the last 35 years in Wisconsin to make sure we have a good calibration and we can trust the numbers the model is producing. So it's the strength of the model, really. We've collected enough data to have faith in the numbers it's producing, whether it be flow or concentrations or how well the stormwater control measures are going to work. So I want to just take you through very briefly some of the analysis we've done, some of the data collection we've done to make this model work. Is our data collection over? Absolutely not. This will go on for some time. We're never going to have the exact answers, obviously. There's too many variables. So I want to emphasize we are continuing to do our work, and I'll share that with you. And that's been a struggle for some of our consultants, too, because every time I change the model, it means maybe the city wants to run the model again. And so we officially froze the model at 9.2, but now we're at 10.1. 10.2.1. And so, but most of the consultants in the presentations I've given have said, yeah, we're gonna go on this trip with you, and we're gonna keep making our analysis better, because we know that every time you change the model, you're making an improvement and probably making what we do more cost effective. So I want to go briefly through with you these different areas that we have to keep studying, whether it be the source areas, the loads from the land uses, or how well the stormwater control measures work. And again, when it comes to the source areas and land uses, Caroline's covered this, but I had the challenge of trying to monitor all of these different source areas in residential, commercial, all the land uses Caroline described, and within each one I had to worry about the rooftops, the driveways, all these kinds of things, and it's been a good thing to do. And then Carolyn has mentioned to you all the types of stormwater control measures the model does. I'll briefly go through street cleaning, grass swales, and hydrodynamic devices, but we have data for most of them that we've been using for calibration and verification. The source area sampling started back in the early 90s, where we decided, well, we had to collect some data for almost every source area, so we developed these little simple source area samplers. The basic idea is that the hole in the top is actually calibrated for the area so they don't fill up right away. And students went out and got the bottle, put the bottles out before the storm, after the storm would collect them. The basic idea was to understand the variability between one type of source areas. Did many streets, many driveways, many rooftops, that kind of thing. Back up here again. And of course, to make it all make sense, you had to monitor the end of the pipe. So we monitored the end of the pipe of these areas so we could say, well, if you put all these numbers into the model from the source areas, do they actually add up to the number at the end of the pipe? And of course, the monitoring here was state-of-the-art monitoring, which we continue today for collecting water samples and flow. So this is just an example of the kind of sites we had through the years. This is 7 sites. You can see that it included residential, commercial, and maintenance yards, industrial. The size of the sites went from 4 acres up to 1,000. Of course, we monitored many more flows than we did concentrations just because of the limitations of the lab costs. But we had a lot of flows and a lot of concentrations. This is just an idea of the kinds of what the land uses look like. Upper left would be medium density residential. Obviously, lower left would be a maintenance yard, and lower right would be kind of a commercial strip. So just your typical kind of land uses. One of the challenges in all data collection is to do something that's kind of average. We're not trying to monitor extreme situations because modeling is mostly about averaging because we can't possibly monitor every kind of situation. So here's the results for measuring volume of runoff. You can see here that, again, looking at about 6 sites, that on a median value we come within is about 5% of the measured volume of runoff for, 75 storms, or Canterbury, we had 55 storms and came within 10%. I account this as being really good. So we're really nailing that flow. As Caroline was saying, she showed you how we do the small storm hydrology. And there's some large events in there too. I'm feeling good about that. I could probably hit some of these sites right on if I wanted to, but remember, we're putting in the runoff coefficient curves or averages. So, but I could make each one perfect if I wanted to, but we're using averages. That's the whole idea of this modeling idea. And here's what some of the plots look like. Predicted runoff on the y-axis and observed runoff on the x-axis. And again, you can see the red dots tend to follow the 45-degree line really well. The lower right is the maintenance yard, and of course the maintenance yard is 100% impervious, and so over a whole range of rainfalls, from small to large, we're essentially right on. And then for Canterbury, lower left, that's 1,000 acres. And again, we're a little bit over, a little bit under, but in modeling, that's sometimes what you're trying to achieve is being a little bit under and a little bit over. So overall, we did really well with the flow. Here's another example. We monitored some 124 rainfalls on some parking lots in middle Wisconsin. And you can see, again, modeled cubic feet versus measured cubic feet. We're coming very close to the measured values. So this is the beginning of building confidence in any model, is you have to get the flow right. If you haven't got the flow right, then you really have to stop and wonder about what you're doing. But right now, I think we're doing a good job with that. Can we make some improvements? Yes, and I continuously work on that. So Carolyn made this list of pollutants. I just want to briefly go through and just show you some of the data there. This is the numbers for TSS for the different source areas in milligrams per liter. You can certainly see there's a difference from one site to another. Lawns tend to come out high, okay? The thing that I'm honest to is when I calibrate the model, I don't change these numbers, okay? Sometimes in calibration, we have to use a delivery factor, okay? Because obviously not everything is transported for every storm. It gets hung up in the storm sewer pipe or in the curb, whatever. But I don't change these numbers. Because what's important to our decision making, as Jim was pointing out, is this relative source, all right? Which are the important sources? If I start changing these numbers to make the model calibrate, we've essentially lost the whole purpose of doing it. Now you notice that the streets is yellow. I put a yellow color with that. Now that's a real concentration, you know, about 180 milligrams per TSS that we see in a residential street, for example. But that's not how the model calculates it. We took a whole different approach to that so that we could actually do street cleaning. And the basic approach is to try to keep track of how much dirt is on the street. And in order to do that, you got to have accumulation curves, which is shown in the upper right-hand corner. So you can see that's different for smooth streets versus intermediate streets, okay? And you also have to have some idea of how much is washed off during each rainfall event. So that really keeps track of how much dirt is on the street and then how much is washed off so that you get a concentration along with all the other source areas when you're running the model. Will this be perfect for every source area? Obviously, but it's way beyond our resources to do that. But for streets, which are such an important source of our pollutant load, we've been able to do that. So again, lower right-hand corner, you see that the model actually predicts a accumulation, then wash off, accumulation, then wash off, a kind of a sawtooth pattern as the different rainfall events are calculated by the model. So for suspended solids, if you look at some of the sites we've done in the past, you can see the median value is about 20%, anywhere from 1% off to about 35% off. Again, I could hit these sites right on, but on the number that's in the model, in the files that Caroline talked about, it's an average from all the sites we did to make sure I'm covering all the variability that's there. And of course, variability we'll talk about in a second is something we're reducing right now, but overall I was doing really well to get that small range of numbers, given that we're doing an averaging process here. And again, the plots look good too. We have on the upper left-hand corner, we have the maintenance yard where we had the flow right on, but obviously there's variability in what's washed off. So again, a little over, a little under. Occasionally there's something happens where they're like the little yellow dot I show you, where something's going on, the model doesn't predict it, underestimated in that case. And that's because somebody I found out dumped, one of the people at the maintenance yard backed up a truck and dumped some dirt they've been collecting right next to the inlet for where we were monitoring. So again, these are the kind of things that you have to be careful of. And the lower right-hand corner, you can see that's Canterbury, where again, we predicted the TSS fairly well, a little over, a little under throughout all the rain events we did. Phosphorus, one of our more important pollutants that we talk about constantly. There's two ways the model has that in the PPD files. One way is the particulate phosphorus, which is the upper bar chart, and then the dissolved phosphorus, which is the lower bar chart. Usually dissolved phosphorus is about 30–40% of the total phosphorus. No surprise there, the lawns have the highest concentration, all the way down to the lower street concentrations, all right? The lawn, of course, when you get into this and think about the kinds of things that Jim was talking about for a TMDL, the lawn might have the highest concentration, but a much lower contribution, because the runoff doesn't occur that often. So then in your pie chart of sources, that high concentration certainly plays a role, but the contribution from the lawns in a residential area might only be 20% on an annual basis. The streets, on the other hand, as Kevin was addressing, for phosphorus, probably that number is going to go up, because now we're doing a lot more work with the seasonal stuff. So that's probably going to change. And for the phosphorus, a median value would be about 30%. We've made real progress in that number from when we started doing this, so I'm feeling good about it. But that number is going to improve, especially when we include the seasonal stuff, and I'll show you more about that in a minute. Remember, the numbers that I've put in the model are an average of an annual data collection process. So all the numbers are just averaged together. So I'm not bringing the seasonal in, but we're going to be bringing the seasonal in. Huh. Come on. That's not working. All right. Okay. Again, plots that show that we're pretty much right on. I can't spend too much time on this or even getting this thing to work. Here's an example, again, where we have a highway where and the runoff was off by about 1 to 2%, and the TSS was off at one site by 30% and another site by 1%. Again, overall doing really well on predicting, even on the highway, what our pollutant load is. On a national basis, Caroline introduced the idea. We're trying to provide a database that could calibrate the model in many different places. When Bob Pitt was doing this, it gave us a chance to add some pollutants that we're just starting to work on more here, like bacteria. So I just wanted to show you some data that came out of that analysis, calibrating the model on a national basis using that national database. You can see, again, you have the model number on the y-axis and the observed numbers on the x-axis, and you can see a TSS, we're doing well. Interesting enough, look at the lower right, we did really well in the bacteria, which is becoming more and more important now. Milwaukee's TMDL certainly has a bacteria component to it. So again, we can use these national databases to help us do better with these other pollutants. So overall, taking a fairly simplistic monitoring method, we're able to develop a model that calibrated and verified really well for most of the land uses that we're considering and giving us a good foundation. We got the flow on very, very well so that, again, we got a good foundation for doing this. But that's just kind of a beginning. We've certainly been working hard since then. One of the crises we had over all the years I've been doing this, and I've been monitoring urban runoff since 1974, was some of the biases that you get in the sampling. And so the last 6 years, we've been working hard on a new method that hopefully the EPA will adopt nationally for stormwater monitoring that removes that bias. And we've written 5 papers on this, and we use it for all our sampling now. So I'm very excited about it. So that the model now pretty soon is going to start seeing the results of some of this monitoring. So but basically we can use it for in pipes. It goes up. You look at the middle picture. The arm goes up and down, and the arm goes up and down, and how far it goes changes based on the depth of flow. This is quite complicated. It took us a long time to get the programming right. The far right, you can see we're monitoring up and down the pipe. It's hard to get to. We can monitor in an open channel in an urban stream where we put the device on the bottom and it goes up and down. And we've been monitoring agricultural fields this way too and seeing some really big differences in how you collect the numbers. So again, a very exciting improvement in what we're doing. And one of the key things for me as a person who's trying to make the model better and look at trends better, it lowers the coefficient of variation dramatically so we can see trends much, much more clearly. I can't go into all that right now, but we've written 2 papers on this now, and it's very exciting to see how the coefficient of variation is improved. So again, we're moving forward. We have a matrix I'm filling out now. We're using the new sampling technique on all the types of things we did before, on all the source areas, the streets and the rooftops and so forth, and on the land uses like shopping centers and residential areas. We're trying to do 2 of those a year, and pretty soon we'll start adding some of the data to the model. It'll make some changes. And of course, to me, very importantly for the phosphorus, we'll add the seasonal component. Most places in our country have this kind of spring-fall thing. And if you look at the green chart I have at the bottom there, at one of our sites, it has a total phosphorus concentration on the y-axis and the time on the x-axis. And you can see in May, when you have the pollen on the street, the concentrations increase dramatically. We're talking about over 2 parts per million. That's amazing. And then when you come into fall, at October 15th, October 31st, again, dramatic, all the way up to 4 parts per million of phosphorus. And right now, the numbers in the model are just an average of all of that. So you can see how my numbers are going to improve once I do it by season. So I'm very excited about that. And again, I know it's hard for the consultants to sometimes keep up with this, but the response so far has been exciting. Yeah, let's keep making this better. So we're going to keep making it better. We can certainly keep our programs going with what we have, but I think these kind of improvements will build even more confidence in our loading estimates and how well our stormwater control measures are working. All right, let's quickly go through a couple of these stormwater control measures. Street cleaning is a primary one I get constant questions about. But along with, let me just stop for a second and say, right now we're studying permeable pavement, bioretention systems, grass swales, leaf management, a very hot item around here, getting credit for leaf management, and we're working very hard on finishing our particle size distribution work so that we get the right particle size distribution. The model can do a different particle size distribution for every source area and every land use. So we're trying to provide those numbers in the best way possible. Okay, street cleaning. We've done 3 major studies on this. We've probably spent over $3 million trying to characterize street cleaning, a very important public works activity that cities should get credit for. Again, the basic idea is that the model develops a sawtooth pattern where you have the accumulation, then the street is cleaned, and then it rains, and up and down, up and down. So it's very important to get some idea of that street load, like I said before. One of the basic ways we do this is we go out with a vacuum cleaner and take wand strips across the street. In our last study of that, the graduate students that work with us collected 2 tons of street dirt that way. So before and after the streets are cleaned, before and after it rains, and doing accumulation studies. So then I can put into the model an accumulation function. In the upper right-hand corner, there's that accumulation function that has a built-in decay function because at some point it starts to reach an asymptote due to wind and cars and so forth. And then I have a wash-off coefficients that usually bounce between like 15 and 30%, and they're a function of rain intensity and the amount of street load you have. So again, obviously more intense storms are going to have a higher runoff coefficient. So we were able to develop those kinds of things with the data we collected. And then last of all, in the street cleaning thing, you have to have a productivity function. How efficient is the machine? So this plot in the upper left-hand corner shows post-cleaning street loads in pounds per curb mile, and the x-axis shows the pre-cleaning street load in pounds per curb mile. And the upper right-hand corner, there's the equation that goes into the model. So it essentially shows you here when the red line crosses the blue line, that's when the street cleaner stops working. So when the street load gets below about 600 pounds per curb mile, the broom sweepers don't work anymore. So that means sometime at the end of the spring, they stop working. Again, the challenge is in order to sort of verify what we're doing, I have to be able to put all this kind of data, the accumulation, the productivity functions into the model and have the model predict the street load with time. So the red line is the model number for a particular site. This is the mechanical broom sweeper in a residential area. And then the blue lines are the measured numbers. So I have these kinds of plots over and over again. So basically the model provides the basic structure. I can put all this data we've collected into the model and say, how well are you matching this? It's very exciting when you see these plots come out this close. So I feel pretty confident that we're hitting the street cleaning thing pretty much right on. And I don't think we're going to do that kind of study anymore. But anyway, so yeah, it works well. The key thing is having that structure so you can put the numbers in there. And so when Bob Pitt originally put that together, he had the structure. What are the variables that drive street cleaning? And he got it right, so we could actually come up with something we believe in. Just to give an example how I can extrapolate this, we were under contract from the San Francisco Bay TMDL. I'm on the technical committee there. And they asked me, well, can you give me street cleaning benefits of PCBs? They certainly have a legacy problem, but the PCBs have spread themselves around the city. So they're finding in their street dirt some high levels of PCBs. So I worked with them for about a year, and they did some monitoring like I just described to you. And we came up with that upper left-hand corner shows you a productivity function we came up with for PCBs. And so they're writing a report now to the EPA which says lower right-hand corner, if they use high-efficiency street cleaners once a week, what PCB reduction will they get? So I think very exciting how you can take this basic structure of the model and collect some data and use it for other things. Obviously, we've never done PCBs, but this gave me a chance to do it. For the hydrodynamic separators, again, people want to use these things in a lot of sampling. These are sites we sample with these kinds of things, monitoring inlet, bypass, outlet. And I always had this goal for myself. I wanted to come with a few percentage points of what the model gave. So you can see here for the storm scepter and vortex, I have a measured TSS reduction of 6% and 25%, and the model predicted 12% and 19%. I was a little flabbergasted, actually. That's pretty close. So it certainly met my standards for feeling some confidence. So again, the structure was there. I could collect some data, and of course, a lot of particle size distribution is a real key thing here, and actually match what's going on. Okay. For LID, that's another important thing that we're all dealing with now. We had a site that we monitored where we had grass swale drainage. We had an infiltration basin precluded by a wet pond, and the idea was to monitor all that. We have a monitoring. You can see here the right-hand side. You can see we monitor the pond and the outlets of the basin, and we had 5 years of data. And I just wanted to show you that in the yellow area, that after the infiltration basin, the monitoring results for 1 year when all the site was developed, 2004 to 2005, we measured 144,000 cubic feet of water coming out, and with a little bit of making sure I had the infiltration right. So the last column there shows I could really easily calibrate the model to the same number. Again, the structure was there, so I could actually get the model to match the measured numbers. So there's the strength of a tool like this. It's a lot of effort. We understand people cannot monitor every site they're going to do a TMDL on. So we've worked hard to make sure that the data that's in the model is as good as it can be, and we keep improving it so that our efforts here to clean up with our TMDLs will be as cost-effective as possible.
Aww.
That was Kevin's idea.
Hey, Wisconsin state animal right there.
Well, yeah, thank you guys all for your time for these presentations. Before we take a couple final questions, I just wanted to remind people there's a post-event or a post-webinar survey. Please take a couple minutes to fill it out and let us know how we can improve future webinars, and also you can use that as a way to ask any additional questions that you may have missed. Also just wanted to offer my email address, dpeckam@neiwpcc.org, if you'd like to follow up about anything, whether it's input or additional questions. So I'm monitoring the chat boxes. One question that we didn't get to cover from earlier, so this one maybe for Caroline or Jim, how do you delineate areas served by municipally owned sewer versus private or no storm sewers?
I'll jump in on that. I know that's an issue with a lot of other municipalities. In Wisconsin, we're fortunate in a way in that if you are an incorporated municipality, and for us that means a city or a village, you cannot be in the incorporated area unless you have sanitary service. So there's kind of a linkage there between sanitary and service and the incorporated boundary. So we don't have this issue of private on-site, treatment systems for domestic sewage. I hope that answers the first question. What was the second thing, Dan?
It was just delineating the municipally owned sewer versus private or no storm sewers.
Yeah. So for storm sewers then, well, if a property discharges into a municipally owned and operated conveyance system, and as Kevin said, that can be a ditch, that can be a pipe, that can be a roadside swale. They are part of the MS4 system if they're connected. So I'm not quite clear how if you have a private system on an industrial site, let's say it is right adjacent to a receiving water or river that never enters the municipally owned system, then that would be a private system that would be non-regulated within the MS4 area.
And when you do your work as a consultant, the municipalities have their mapped out storm sewer systems, so you overlay that with the land use and your watersheds and then make those corrections.
Well, and as part of their permit, and every city their permit has to submit a map of their system, but Wisconsin or elsewhere all do that.
So I know we're right up at 4 o'clock and want to be mindful of everyone's time. Maybe just one final question to conclude. Sort of touched on this a couple of times, but what are the typical measures and activities that generally are conducted by MS4s to achieve the 20% required reduction beyond the base MS4 program? And sort of connected to that, how much credit is given to the base program?
So I think, with the beauty of this analysis, I think it varies substantially. Some municipalities may be relying on street sweeping a lot. Like, for example, if you're in a highly urbanized area, historic development, they may be using street sweeping, catch basins, porous pavement, the hydrodynamic devices that Roger mentioned. As you move out into newer development areas, they're using a lot of swale systems, wet detention ponds. It all comes down to land use and space to put practices in.
And one of the things we find, I'll just quickly add, is that in the street cleaning scenarios, you find out that cleaning the streets outside of the spring and fall times don't provide a lot of benefit to pollution control. You may do it for other reasons, for aesthetics, but as far as sediment control goes, it's not the time of year to be doing the concentrated cleaning practices. It's spring and fall make the difference, and that's reflected both in the monitoring and in the modeling for a municipality.
So another thing, Dan, before we probably sign off, is I know webinars like this can be challenging for the Q&A portion. So if you have a lot more questions that came in writing, or if additional people want to send you questions, feel free to send those to myself, and then I'll run them through the group here, and we'll write up responses, and then you can mail that back out.
Yeah, that sounds fantastic. Thank you, Kevin. I appreciate you offering to do that in addition to presenting. I'll probably conclude with thanking our 4 presenters for today, and thanking all of you for dialing in. Really appreciate your time, and we'll be in touch with follow-up regarding the recording of the webinar to all attendees and the various lists that we've advertised this to, and then also regarding the questions that we weren't able to cover. So apologize that we weren't able to get to all the questions, but we got through a number of them, and we'll do our best to answer the remaining ones that were written to the chat boxes or any other ones that people fill out in the post-event survey. So thank you again, everyone, and we'll sign out for now.
Yeah. Thanks, Dan.
Thank you.
Bye.